What if everything you've ever been told about the fundamental nature of reality is wrong? What if the solid matter you're touching right now, the device in your hands, even your own body, isn't actually made of matter at all, but is instead frozen light? What if atoms, those supposedly fundamental building blocks we learned about in school, are just elaborate illusions created by light particles dancing in specific patterns? I'm about to share something that will fundamentally change how you see the world around you. In 1905, Albert Einstein published a paper that would eventually win him the Nobel Prize. But buried in that work was an equation so profound that physicists are still unraveling its implications today. That equation, E equals mc, doesn't just tell us that energy and matter are related. It tells us they're the same thing. Matter is energy, and light is pure energy. Here's the kicker that will set the stage for everything we're about to explore. In quantum field theory, the most successful scientific theory ever created, particles aren't actually particles at all. They're excitations in fields of energy. And photons, particles of light, can literally transform into matter particles and back again. This isn't science fiction. This happens billions of times per second in particle accelerators around the world. Light becomes matter. Matter becomes light. So what if we've had it backwards this whole time? What if light isn't just something that bounces off atoms? What if light is the atom? Before we dive deeper into this reality-shattering concept, do me a favor. If this introduction has already got your mind spinning, hit that like button and subscribe, because over the next 3 hours, I'm going to take you on a journey that will permanently change how you perceive reality itself. Also, drop a comment telling me what country you're watching from and what time it is where you are right now. I want to know how this idea is spreading across the world as we speak. Let's start with what you think you know about atoms. You probably learned in school that atoms are made of protons, neutrons, and electrons. Protons and neutrons sit in the nucleus, solid little balls of matter, while electrons orbit around them like planets around a sun. Right? Wrong. That model is so outdated, it's almost criminal that we still teach it. That's the Bohr model from 1913, and while it was revolutionary for its time, it's about as accurate as saying the Earth is flat. Here's what atoms actually look like, and this is where things start getting weird. Atoms are almost entirely empty space. If you scaled up an atom to the size of a football stadium, the nucleus would be smaller than a marble sitting at the 50-yard line. The electrons? They wouldn't be tiny balls orbiting around. They'd be probability clouds, fuzzy regions of space where the electron might be if you looked for it. But here's where it gets interesting. What are those electrons made of? According to the standard model of particle physics, our best current understanding of reality, electrons are fundamental particles. That means they're not made of anything smaller. They're point-like, with literally zero size. They're pure, concentrated ... what exactly? This is where most physics textbooks get suspiciously vague. They'll tell you electrons have properties like mass, charge, and spin, but they won't tell you what an electron actually is. And there's a good reason for that. We don't know. Or rather, we know something so strange that it sounds like mysticism when you say it out loud. Electrons are excitations in the electron field. That's not a metaphor. According to quantum field theory, there's an electron field that permeates all of space, and what we call an electron is just a ripple in that field. Think of it like a wave on the ocean. The wave isn't a separate thing from the ocean. It's just the ocean, shaped in a particular way. Now, here's where light enters the picture in a way that should make you pause. Photons, particles of light, work exactly the same way. They're excitations in the electromagnetic field. A ripple in a different field, but fundamentally the same type of thing as an electron. In 1930, a brilliant physicist named Paul Dirac made a discovery that changed everything. He was trying to combine quantum mechanics with Einstein's special relativity, and his equations kept predicting something impossible. They predicted that for every particle, there should be an antiparticle, identical in every way except with opposite charge. At first, physicists thought this was just a mathematical quirk, an error in the equations. But in 1932, Carl Anderson discovered the positron, the antiparticle of the electron, in cosmic ray experiments. Dirac's prediction was correct. And here's the mind-bending part. When a particle meets its antiparticle, they annihilate each other and turn into pure energy, into light. 2 photons, to be precise. An electron and a positron, 2 supposedly solid bits of matter, can collide and completely convert into electromagnetic radiation. Nothing is left behind. The mass is gone. The matter is gone. Only light remains. But the reverse is also true, and this is crucial. If you have enough energy, you can create matter out of light. Take 2 photons with sufficient energy, collide them together, and you can produce an electron and a positron. Light becomes matter. This process, called pair production, happens constantly in the universe. Near black holes, in the vacuum of space, in particle accelerators. Light and matter are constantly transforming into each other. So let me ask you this. If matter can turn into light, and light can turn into matter, and they can do this freely and constantly, which one is really the fundamental thing? Is matter made of matter that sometimes becomes light? Or is matter just light that's been trapped in a stable pattern? Let me take you back to 1900, to a problem that was driving physicists absolutely insane. It was called the ultraviolet catastrophe, and it threatened to destroy all of physics as they knew it. Here's the problem. When you heat up an object, it glows. Heat it a little, it glows red. Heat it more, it glows white. Heat it even more, it glows blue. Classical physics had equations that predicted how much light at each wavelength a hot object should emit. There was just one tiny problem. Those equations predicted that hot objects should emit infinite amounts of ultraviolet light. Infinite. Obviously, this wasn't happening. If it were, every campfire would instantly kill you with a blast of infinite radiation. On December 14, 1900, a German physicist named Max Planck presented a solution so radical that he himself didn't believe it at first. He proposed that light couldn't be emitted in any amount. It had to come in discrete packets, which he called quanta. Light wasn't a continuous wave that could have any energy. It came in chunks, like coins rather than a fluid you could pour. The energy of each chunk, each quantum of light, was proportional to its frequency. High-frequency light like blue or ultraviolet came in larger energy chunks. Low-frequency light like red came in smaller chunks. This simple assumption fixed the ultraviolet catastrophe, but it did something much more profound. It suggested that light, which everyone knew was a wave, thanks to countless experiments, also behaved like a particle. Planck himself thought this was just a mathematical trick, not a statement about reality. But in 1905, Einstein took Planck's idea seriously. He used it to explain something called the photoelectric effect, where light hitting metal could knock electrons loose, but only if the light was above a certain frequency. No matter how bright you made red light, it wouldn't knock electrons loose. But even dim blue light would do it. Einstein said this was because light really did come in particles, in quanta, which we now call photons. Each photon carried a specific amount of energy based on its frequency. Red light photons didn't have enough energy per photon to knock an electron loose, no matter how many of them you threw at the metal. Blue light photons did. This won Einstein the Nobel Prize, not his work on relativity. Now, here's where things get really strange. If light behaves like a particle, what about matter? In 1924, a French graduate student named Louis de Broglie asked a simple but profound question in his PhD thesis. If light waves can behave like particles, can particles behave like waves? He proposed that every particle has a wavelength associated with it, given by Planck's constant divided by its momentum. For large objects like baseballs or people, This wavelength is so tiny, it's unmeasurable. But for tiny objects like electrons, the wavelength is significant. 3 years later, in 1927, Clinton Davison and Lester Germer proved Broglie right. They shot electrons at a crystal and saw them form an interference pattern, something only waves do. Electrons were waves, except they were also particles. They were both or neither, depending on how you looked at them. This is wave-particle duality, and it's not just a quirky property of quantum mechanics. It's telling us something fundamental about the nature of reality. Matter and light aren't different types of things. They're the same type of thing viewed from different angles. Think of it like this. Imagine you have a coin. If you look at it face on, you see a circle. If you look at it edge on, you see a line. The coin isn't sometimes a circle and sometimes a line. It's always a coin. But depending on your perspective, it looks different. Matter and light are like that. They're always the same fundamental thing, but depending on how we measure them, they appear as waves or particles. But what is that fundamental thing? What is the coin itself, not just the circle or line we see? The answer that's emerging from modern physics is startling. It's all fields. All of space is filled with quantum fields, one for each type of particle. The electromagnetic field for photons, the electron field for electrons, the quark fields for quarks. When these fields oscillate in certain stable patterns, we call those patterns particles. An electron is a stable vibration in the electron field. A photon is a vibration in the electromagnetic field. But here's what should blow your mind. These fields can interact with each other. They can transfer energy between each other. And under the right circumstances, a vibration in one field can transform into a vibration in another field. That's what pair production is. That's what annihilation is. The fields are dancing together, and sometimes the dance changes which partner is leading. Let me tell you about one of the most famous experiments in physics, one that demonstrates just how bizarre this light-matter relationship really is. It's called the double-slit experiment, and it's been called the central mystery of quantum mechanics. Here's how it works. You take a light source, a barrier with two narrow slits in it, and a screen behind the barrier. You shine light through the slits onto the screen. What do you see? You see an interference pattern. Bright and dark bands on the screen. This makes perfect sense if light is a wave. The light wave goes through both slits, and on the other side, the waves from each slit overlap. Where two peaks meet, you get a bright band. Where a peak meets a trough, they cancel out and you get a dark band. This is exactly what happens with water waves, sound waves, any kind of wave. Now, turn down the intensity of your light source so low that only one photon is going through at a time. Common sense says that each photon has to go through one slit or the other. It can't go through both. So you should just get two bright bands on the screen, one behind each slit. But that's not what happens. You still get the interference pattern. Even though you're sending photons through one at a time, even though each photon is supposedly going through just one slit, somehow they're still interfering with something to create the pattern. The standard interpretation is that each photon goes through both slits simultaneously as a wave, interferes with itself, and then hits the screen as a particle. The photon is in a superposition of going through both slits until it's measured. But here's where it gets even weirder. Put a detector at each slit to see which one the photon actually goes through. The moment you do this, the interference pattern disappears. You get two bands, one behind each slit, exactly what common sense predicts. The act of measuring which slit the photon goes through changes its behavior. It stops being a wave and starts being a particle. This isn't just true for photons. Do the same experiment with electrons, atoms, even molecules with hundreds of atoms. Same result. They all show wave-particle duality. They all act like waves until you measure them. Then they act like particles. In 1978, John Wheeler proposed a variation called the delayed choice experiment. The idea is this: set up the double slit experiment, but don't decide whether to measure which slit the particle goes through until after it's already passed through the slits, but before it hits the screen. Common sense says it shouldn't matter. The particle already went through one slit or both. Your choice to measure or not can't change the past. But when experimenters actually did this in the 1980s and 1990s, they found that Wheeler was right. Your choice to measure or not, made after the particle passed through the slits, determines whether it went through one slit or both. The particle's past is not determined until you measure it in the present. Let me repeat that because it's important. The particle's past, what actually happened, is not determined until you make a measurement in the present. The universe doesn't just have an uncertain future, it has an uncertain past. Now, here's why this matters for our question about whether light is the building block of atoms. These experiments show us that particles, whether they're photons or electrons, don't have definite properties until they're measured. They exist in a state of superposition, being multiple things at once. An electron in an atom doesn't have a definite position. It's smeared out over the entire atom, existing in all possible positions simultaneously as a probability cloud. Only when you measure it does it collapse into being at one specific location. This means that the electron, this supposedly solid bit of matter that makes up atoms, isn't actually sitting somewhere in the atom. It's everywhere in the atom at once. It's not a thing with a location. It's a field of possibilities. And here's the crucial insight. Photons work exactly the same way. A photon isn't a little ball of light traveling through space. It's a ripple in the electromagnetic field, and that ripple is also smeared out over space as a probability wave until it's measured. Electrons and photons are the same type of entity. They're both quantum fields in superposition states. The only difference is which field they're in and what properties they have. But fundamentally, they're both the same kind of mathematical object in quantum field theory. So when we ask whether light is the building block of atoms, we're asking the wrong question. Light and matter aren't different things that build each other. They're different manifestations of the same underlying quantum field structure of reality. Before we go deeper, I need you to do something for me. If you're still with me, if your mind is already reeling from these revelations, hit that subscribe button, because we're about to go much deeper. We're about to explore ideas that will make what we've covered so far seem simple. And I promise you, by the end of this journey, you will never see reality the same way again. Also, leave a comment with the most mind-blowing thing you've learned so far. I read every single comment. Now let's talk about something that sounds like complete science fiction, but is absolutely real. Vacuum energy and virtual particles. You probably think of the vacuum of space as empty. Nothing there, just void. But according to quantum field theory, the vacuum is anything but empty. It's seething with activity. Remember those quantum fields we talked about? The electron field, the electromagnetic field, all the others? Those fields are everywhere, even in empty space. And because of the uncertainty principle discovered by Werner Heisenberg in 1927, these fields can never be completely still. They're always fluctuating, always vibrating with what's called zero-point energy. These fluctuations are so energetic that they can briefly create pairs of particles and antiparticles out of nothing. A photon in the electromagnetic field can fluctuate into an electron and a positron for a tiny fraction of a second. Then they annihilate back into the electromagnetic field. These are called virtual particles. Now, you might think these virtual particles are just a theoretical concept, a mathematical tool, but they're not. They have measurable effects on the real world. In 1948, a Dutch physicist named Hendrik Casimir predicted something strange. If you put two metal plates very close together in a vacuum, the vacuum energy between them would be different from the vacuum energy outside them. The plates would restrict which wavelengths of virtual photons could exist between them. This difference in vacuum energy would create a tiny attractive force pushing the plates together. This is insane. There's nothing between the plates, just vacuum. But because the vacuum isn't truly empty, because it's full of fluctuating fields creating virtual particles, these empty plates should be pushed together by literally nothing. In 1997, Steve Lamoureux measured the Casimir effect with high precision and found it exactly matched the prediction. The vacuum, empty space itself, exerts a force on objects. The nothing between the plates is pushing them together. What does this mean? It means that the distinction between something and nothing, between matter and vacuum, isn't as clear as we thought. The vacuum is full of potential particles, virtual particles popping in and out of existence. And real particles, the ones that make up atoms, are just excitations in the same fields that create these virtual particles. An electron in an atom is just a virtual electron that lasted. A photon from a light bulb is just a virtual photon that became real. The only difference between a real particle and a virtual particle is how long it lasts. Here's where this connects to our central question. If the vacuum is constantly creating particle-antiparticle pairs, constantly creating matter and antimatter from pure energy, then matter isn't some separate, stable stuff. Matter is just temporary condensations of energy from the quantum fields. And what is energy? In the case of electromagnetism, energy is light. The electromagnetic field is the photon field. When an electron-positron pair pops into existence from the vacuum, they're being created from virtual photons, from the electromagnetic field. In a very real sense, matter is continuously being created from light-like fluctuations in the vacuum, and then destroying itself back into light-like fluctuations. This is happening everywhere, all the time, right now in the space between atoms in your body. Let's talk about what's inside atoms, because this is where things get truly mind-bending. You know that atoms have nuclei made of protons and neutrons. But what are protons and neutrons made of? In the 1960s, physicists discovered that protons and neutrons aren't fundamental particles. They're made of smaller particles called quarks. A proton contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. But here's the strange part. If you add up the masses of the 3 quarks in a proton, you only get about 1% of the proton's total mass. 1%. So where's the other 99% of the mass coming from? It's coming from light. Well, not exactly light, but something very similar. It's coming from gluons, the particles that carry the strong nuclear force that holds quarks together. And gluons, like photons, are massless particles. They're pure energy, traveling at the speed of light inside the proton. The interior of a proton is a churning sea of gluons and virtual quark-antiquark pairs, all moving at near light speed, all created from the binding energy holding the proton together. And according to Einstein's E equals mc, this energy has mass. The energy of these massless gluons zipping around inside the proton is what gives the proton 99% of its mass. This is profound. You are made of atoms. Atoms are mostly empty space with nuclei at their centers. Those nuclei are made of protons and neutrons. And protons and neutrons are made of quarks held together by gluons. But the mass, the actual substance of the proton, is almost entirely from the kinetic energy of massless gluons. You are made of trapped light and its kinetic energy. But it gets even stranger. In 2012, physicists at CERN discovered the Higgs boson, the particle associated with the Higgs field. The Higgs field is what gives fundamental particles their mass. Electrons, quarks, and other fundamental particles get their mass by interacting with the Higgs field that permeates all of space. Think of it like this. Imagine you're walking through air. Easy. Now imagine walking through water. Harder. Now imagine walking through honey. Much harder. The different substances resist your motion differently. They give you an effective mass, a resistance to acceleration. The Higgs field does this for particles. Particles that interact strongly with the Higgs field, like electrons and quarks, have mass. They resist acceleration. Particles that don't interact with the Higgs field, like photons, have no mass. They always travel at the speed of light and can never be slowed down or stopped. So even the tiny 1% of a proton's mass that comes from the quarks themselves isn't really intrinsic mass. It's coming from the interaction between the quarks and the Higgs field. It's coming from energy, just a different type of energy than the kinetic energy of the gluons. When you dig down to the absolute bottom, there's nothing solid anywhere. No little billiard balls, no hard stuff, just fields, vibrations, and energy. The electron is a vibration in the electron field that has mass because it interacts with the Higgs field. The proton is a bound state of quarks held together by gluons, and most of its mass comes from the kinetic energy of those massless gluons. And photons? Photons are vibrations in the electromagnetic field that don't interact with the Higgs field, so they have no mass and travel at light speed. Here's what should blow your mind. All of these fields, the electron field, the quark fields, the electromagnetic field, the Higgs field, they're all fundamentally the same type of mathematical object. They're all quantum fields. The universe is just quantum fields, oscillating in different patterns, interacting with each other in specific ways defined by the laws of physics. Some oscillations we call matter, some we call light, some we call force carriers, but they're all just vibrations in fields. The universe is music, and particles are the notes. Let me tell you about something that sounds completely absurd, but is absolutely true: quantum tunneling. This is one of the most important quantum effects, and it reveals something profound about the nature of matter and energy. In classical physics, if you roll a ball at a hill, the ball needs enough energy to get over the top. If it doesn't have enough energy, it rolls back down. It can't spontaneously appear on the other side of the hill. That would violate conservation of energy. But in quantum mechanics, particles can do exactly that. An electron facing an energy barrier it doesn't have enough energy to overcome can still sometimes appear on the other side. It tunnels through the barrier. This isn't just theoretical. Quantum tunneling is why the sun shines. The protons in the sun's core don't have enough energy to overcome the electromagnetic repulsion between them and fuse together. Classically, the sun shouldn't work. But because of quantum tunneling, protons can tunnel through the energy barrier and fuse anyway. Every photon you see from the sun exists because quantum tunneling made nuclear fusion possible. Quantum tunneling is also how radioactive decay works. Alpha particles trapped inside a nucleus don't have enough energy to escape, but they tunnel through the energy barrier anyway. It's why transistors work at small scales. It's everywhere in quantum mechanics. But here's the key insight. Tunneling is possible because particles aren't really particles. They're waves, probability distributions. The wave function of an electron facing a barrier doesn't stop at the barrier. It extends through and beyond it, just with a much smaller amplitude. There's a small but non-zero probability the electron is on the other side. And sometimes, when you measure where the electron is, you find it there. The electron didn't travel through the barrier. It didn't need to have enough energy to climb over. It was simultaneously on both sides as a probability wave until measurement collapsed it to one side or the other. This is only possible because the electron and all particles are fundamentally fields with wave-like properties, and the same is true for photons. In fact, there's a phenomenon called photon tunneling where light can tunnel through barriers too. If you have two pieces of glass separated by an air gap, light will mostly reflect off the first piece of glass when it hits the air gap at a certain angle. But some light will tunnel across the gap and emerge from the second piece of glass. The photon probability wave extends through the gap, even though classically the photon doesn't have the right properties to cross it. Matter and light, once again, behaving in exactly the same way because they're exactly the same type of thing. Quantum field excitations with wave properties. Now I want to blow your mind with something even stranger: quantum entanglement and what it reveals about the nature of reality. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper arguing that quantum mechanics must be incomplete. They described a thought experiment, now called the EPR paradox. The idea is this: create two particles that are entangled, meaning their quantum states are correlated. Send these particles far apart. Quantum mechanics says that until you measure one particle, it doesn't have a definite state. It's in a superposition of multiple states. But as soon as you measure one particle, you instantly know the state of the other particle, no matter how far away it is. Einstein hated this. He called it spooky action at a distance. He argued that the particles must have had definite states all along, and we just didn't know what they were. There must be hidden variables that determine the particles' states from the beginning. In 1964, a physicist named John Bell proved mathematically that if hidden variables exist, certain statistical correlations between measurements on entangled particles must satisfy an inequality, now called Bell's inequality. If quantum mechanics is right, and there are no hidden variables, that inequality will be violated. Starting in the 1970s and continuing through today, experimenters have tested Bell's inequality thousands of times with increasingly sophisticated setups. Every single time, Bell's inequality is violated. Quantum mechanics is right. There are no hidden variables. The particles really don't have definite states until they're measured. But here's the truly mind-bending part. When you measure one entangled particle, the other particle's state is determined instantly, faster than light could travel between them. This isn't just a correlation that was there from the beginning. The particles are genuinely connected across space in a way that defies classical understanding. In 2022, the Nobel Prize in Physics was awarded to Alan Aspect, John Clauser, and Anton Zeilinger for their work demonstrating entanglement and violating Bell's inequalities. This is established science now. What does this mean? It means that entangled particles aren't really separate. They're part of a single quantum system, even when they're light years apart. The universe doesn't just connect things through forces and signals traveling through space. Things are directly connected at a quantum level in ways that transcend space. And here's where light comes in. Some of the most powerful demonstrations of entanglement use entangled photons. You can create two photons that are entangled in their polarization. Measure the polarization of one, and you instantly determine the polarization of the other. These entangled photons can be sent in different directions. They can be separated by kilometers, miles, even in principle by the width of the universe. But they remain a single quantum system. They're not two separate things. They're one thing, expressed in two locations. This tells us something profound about light and matter. The individuation of particles, the fact that we think of them as separate objects, is an illusion. At the quantum level, particles that have interacted are forever entangled, forever part of a larger whole. Every atom in your body has interacted with countless other atoms. The photons those atoms emitted have traveled across the universe and interacted with other atoms. At a deep level, everything in the universe is entangled with everything else. We're all part of one vast quantum system. The separation you feel between yourself and the world, between your body and the chair you're sitting in, between you and the stars, is a classical illusion. At the quantum level, we're all connected. We're all part of the same quantum fields, the same fundamental reality. Let me take a brief pause here, because we're almost halfway through this journey, and I want to make sure you're still with me. If you've made it this far, you're in the minority. YouTube analytics tell me that most people have clicked away by now. But you're still here, which means you're genuinely curious about the nature of reality. That makes you special. Do me a favor. Hit that like button if you haven't already. And if you know someone who would appreciate this deep dive into the fundamental nature of reality, share this video with them. These ideas are too important to keep to yourself. Now, let's go even deeper. I want to talk about something that will challenge everything you think you know about time and causality. The concept of retrocausality in quantum mechanics and what it means for the relationship between light and matter. We talked earlier about Wheeler's delayed choice experiment, where your decision to measure which slit a photon goes through, made after it already passed the slits, determines whether it went through one slit or both. This suggests that the present can influence the past. But there's something even stranger called the quantum eraser experiment, first proposed in the 1980s and experimentally confirmed in the 1990s. Here's how it works. You do a double-slit experiment with photons, but you mark which slit each photon goes through using entanglement. You entangle each photon with another photon, and by measuring the entangled partner, you can tell which slit the original photon went through. When you do this, the interference pattern disappears, just like putting a detector at the slits. But here's the trick. You don't measure the entangled partner photons right away. You let them travel a long distance first. And you set up your experiment so that the original photons hit their screen and then create their pattern before you measure their entangled partners. Now you have a choice. You can measure the entangled photons in a way that reveals which path information, telling you which slit each original photon went through. Or you can measure them in a way that erases the which path information, making it fundamentally impossible to determine which slit each photon went through, even in principle. The result is staggering. If you measure in a way that preserves which path information, the original photons on their screen form two bands, no interference. If you measure in a way that erases which path information, the original photons form an interference pattern. But remember, the original photons already hit their screen before you made your measurement choice. The pattern they formed was determined before you decided how to measure. Yet somehow, your future choice determined their past pattern. How is this possible? The only way it makes sense is if the photons don't have a definite past. Their history, whether they went through one slit or both, isn't determined until all measurements are complete. Time isn't flowing forward in a simple linear way. The future is reaching back and influencing the past. This has profound implications for our understanding of light and matter. If particles don't have definite histories, if their past is contingent on future measurements, then they don't exist as discrete objects moving through space and time. They're smeared out across space-time, connections between events rather than things that travel between events. A photon going from the sun to your eye doesn't travel through space for 8 minutes. That's the classical picture. In the quantum picture, the photon is a connection between an emission event on the sun and an absorption event in your eye. It doesn't have a path it took. It took all possible paths simultaneously until the full interaction is complete. This is summed up beautifully in Feynman's path integral formulation of quantum mechanics. Developed by Richard Feynman in the 1940s, Feynman showed that you can calculate the probability of a quantum event by summing up the contributions from every possible path the particle could take between the start and end points. Not just the straight line path, every path. Paths that zigzag wildly, paths that go backwards in time, paths that loop around. All of them contribute to the final probability. A photon going from A to B doesn't choose a path. It explores all paths, and the interference between all these paths determines where it's likely to end up. The photon is the sum of all possibilities, collapsing into one reality only when the full interaction is complete. This is true for electrons too, for quarks, for all particles. They're not objects that exist at points in space and time, following trajectories. They're quantum amplitudes smeared across spacetime, connecting events. And if that's true, then the distinction between light and matter becomes even more blurred. Both are just quantum field excitations connecting events in spacetime. Neither exists in a way we intuitively think objects exist. Let's talk about antimatter, because it reveals something shocking about the symmetry between light and matter. When Dirac predicted antimatter in 1930, his equations actually told him something even stranger than he initially realized. His equations showed that an antiparticle, like a positron, is mathematically equivalent to its corresponding particle, like an electron, moving backwards in time. Think about that. A positron moving forward in time is mathematically identical to an electron moving backward in time. In 1940, Feynman took this seriously and developed an interpretation where antiparticles are just particles moving backward through time. In a Feynman diagram, which is a visualization of particle interactions, you can draw a positron moving forward in time, or you can draw an electron moving backward in time. They're the same thing. This leads to a bizarre but mathematically consistent picture. Imagine an electron is created, moves forward in time, then encounters a high-energy photon. That photon has enough energy to create an electron-positron pair. So now you have three particles, the original electron, plus a new electron, and a positron? But in Feynman's picture, you can interpret this differently. The original electron absorbs the photon and reverses direction in time, becoming a positron moving forward. Then it reverses direction again, becoming an electron moving forward again. It's the same electron, just looping back and forth in time. From a certain perspective, there's only ever one electron, just moving forward and backward through time, appearing as multiple electrons and positrons, depending on which direction through time it's going. John Wheeler once speculated, half seriously, that maybe there's only one electron in the entire universe, zigzagging back and forth through time, and all the electrons and positrons we see are just different moments in that one electron's journey. This is probably not literally true for various technical reasons, but it illustrates something important. Particles and antiparticles are two sides of the same coin, and their creation and annihilation, their transformation into and from photons, is so fundamental that we can describe it as motion through time. When an electron and positron annihilate into photons, you can think of it as the electron reversing its direction through time at that point. When a photon creates an electron-positron pair, you can think of it as an electron's world line looping back on itself. Light and matter are so intertwined, so deeply connected, that their transformations into each other can be understood as changes in temporal direction. They're not separate substances. They're different aspects of the same underlying reality. Now let's talk about something that will really bend your mind, the holographic principle and what it suggests about the nature of reality. In the 1970s, Jacob Bekenstein and Stephen Hawking made a remarkable discovery about black holes. They found that black holes have entropy, a measure of disorder or information. But the entropy of a black hole isn't proportional to its volume, as you'd expect. It's proportional to the surface area of its event horizon. This is bizarre. Imagine you have a box full of gas. The entropy of the gas is proportional to the volume of the box. More space, more ways to arrange the gas molecules, more entropy. That's how entropy works for everything we're familiar with. But for black holes, it's different. The amount of information a black hole can contain is determined by its surface area, not its volume. It's as if all the information about what's inside the black hole is somehow encoded on its two-dimensional surface. In the 1990s, Leonard Susskind and Gerard 't Hooft took this idea further. They proposed the holographic principle, the idea that our three-dimensional universe might actually be a projection from information encoded on a two-dimensional surface at the boundary of the universe. Think of a hologram. It's a two-dimensional image that contains three-dimensional information. When you look at it, you see depth, but all the information is actually encoded in the flat surface. The holographic principle suggests that our universe works the same way. Everything you see in three dimensions, all the matter and light and fields, is actually information encoded on a two-dimensional boundary, projected into the three-dimensional space we experience. This has been developed into something called the AD-CFT correspondence, discovered by Juan Maldacena in 1997. It's a precise mathematical relationship between a gravitational theory in a space with a certain number of dimensions and a quantum field theory on the boundary of that space with one fewer dimension. This isn't just philosophy. It's been used to solve real problems in physics. Calculations that are impossibly difficult in one description become tractable in the other. What does this mean for light and matter? If the holographic principle is correct, then three-dimensional particles don't really exist. What we interpret as particles moving through three-dimensional space are actually patterns in a two-dimensional quantum information structure at the boundary of the universe. The distinction between light and matter, between different types of particles, is a feature of the three-dimensional projection. In the underlying two-dimensional theory, they might be the same type of object, just appearing different in the emergent three-dimensional description. You are not a three-dimensional being made of particles. You're a pattern of information on a two-dimensional surface, experienced as three-dimensional. The light entering your eyes, the atoms in your body, they're all the same fundamental information, just processed differently by the holographic projection that creates the illusion of three-dimensional space. This is where physics starts to sound like mysticism, but it's grounded in rigorous mathematics and has passed every test we've thrown at it within the contexts where it applies. I want to take a moment to address something you might be feeling right now: confusion, disorientation, a sense that the solid ground of reality is slipping away beneath your feet. That's normal. That's exactly what you should be feeling. Because what we're discovering is that reality isn't what you thought it was. It's not solid. It's not made of stuff. It's made of ... information, probability, quantum fields, mathematics. Here's what I want you to understand. This isn't just abstract physics that doesn't matter to your daily life. This is your daily life. Every time you look at anything, photons are carrying information from that object to your eyes. But those photons aren't little balls of light bouncing off objects. They're excitations in the electromagnetic field, quantum connections between emission and absorption events. The objects you're looking at aren't made of solid matter. They're made of atoms, which are mostly empty space, held together by electromagnetic forces carried by virtual photons, with mass that comes mostly from the kinetic energy of gluons, moving at light speed inside protons and neutrons. You are not a solid thing interacting with other solid things. You're a pattern of quantum fields, entangled with all the quantum fields around you, all of it arising from deeper structures that might be two-dimensional information at the boundary of the universe. The distinction between you and the world, between light and matter, between energy and mass, these are all high-level emergent descriptions of something much stranger and more unified at the base level. Before we continue, if you're still with me, if you're brave enough to follow this rabbit hole all the way down, hit that subscribe button. Because we're about to go to places that will challenge not just your understanding of physics, but your understanding of consciousness, free will, and what it means to exist. Let's talk about symmetry, because symmetry is one of the most powerful concepts in modern physics, and it reveals a deep truth about the relationship between light and matter. In physics, a symmetry is a transformation you can apply to a system that leaves the laws of physics unchanged. For example, the laws of physics are the same whether you're here or on the other side of the galaxy. That's translational symmetry. The laws are the same whether it's Tuesday or Friday. That's time symmetry. The laws are the same whether you're facing north or south. That's rotational symmetry. These symmetries aren't just convenient properties. They're fundamental. And through a theorem proved by Emmy Noether in 1915, we know that every symmetry corresponds to a conservation law. Time symmetry gives us conservation of energy. Space symmetry gives us conservation of momentum. Rotational symmetry gives us conservation of angular momentum. But there's a deeper symmetry called gauge symmetry, and it's absolutely crucial for understanding light and matter. The electromagnetic force, carried by photons, arises from a gauge symmetry called U1 gauge symmetry. This is a symmetry in the phase of quantum wave functions. You can rotate the phase of the electron field at every point in space, and as long as you do it in a specific way, the physics doesn't change. But maintaining this symmetry requires the existence of a force field. That force field is the electromagnetic field. Photons are the quanta of this field. In other words, photons exist because of the symmetry. The electromagnetic force, light itself, is the universe's way of maintaining a mathematical symmetry. The strong nuclear force, carried by gluons, arises from a more complex gauge symmetry called SU3. The weak nuclear force, carried by W and Z bosons, arises from SU2 gauge symmetry. All the fundamental forces arise from gauge symmetries. Matter particles, like electrons and quarks, exist in representations of these symmetry groups. Their properties, their charges, their interactions are all determined by how they transform under these symmetries. Here's the profound point. Matter and forces, particles and light, they're all emerging from the same underlying mathematical structure. They're all required by the same symmetries. You can't have matter without forces. You can't have electrons without photons. They're two sides of the same symmetrical whole. In the 1960s and 70s, physicists unified the electromagnetic and weak forces into something called the electroweak force. They showed that above a certain energy, these two forces are actually one force. The photon and the W and Z bosons are all manifestations of the same underlying electroweak symmetry, which is broken at low energies by the Higgs field. Physicists are working on grand unified theories that would unify the electroweak force and the strong force into a single force at even higher energies. And beyond that, theories like string theory aim to unify all forces, including gravity, into one fundamental framework. If these theories are correct, then at the highest energies, at the most fundamental level, there's only one force, one field, one symmetry. All the different particles and forces we see are just different ways this one underlying thing can manifest itself at lower energies. Light and matter aren't different things. They're different broken symmetries of the same unified field. They're different notes in the same universal symphony, all arising from one fundamental tone. Let me tell you about something that connects all of this to consciousness and observation: the measurement problem in quantum mechanics. We've talked about how particles exist in superposition, being in multiple states at once until they're measured. But what counts as a measurement? What causes the wave function to collapse? This is one of the deepest unsolved problems in physics. The equations of quantum mechanics describe wave functions evolving smoothly over time, existing in superpositions. But the act of measurement seems to break this smooth evolution and force the wave function to pick one state. In the standard Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s, measurement causes collapse. But this raises an obvious question. What counts as a measurement? Does it require a conscious observer? Does consciousness play a role in collapsing wave functions? Some physicists, like Eugene Wigner, argued that consciousness must play a role. Others, like Hugh Everett, proposed the many worlds interpretation, where wave functions never collapse. Instead, every possible outcome happens, but in different branches of the universe. When you measure a particle, the universe splits into multiple versions, one for each possible outcome. Another interpretation, called decoherence, suggests that wave functions don't really collapse. Instead, interactions with the environment cause different outcomes to become disconnected from each other, so they can't interfere. From inside any one outcome, it looks like collapse happened, but really all outcomes still exist, just separated by decoherence. We don't know which interpretation is correct. We might never know. But here's what all interpretations agree on: observation, interaction, measurement, whatever you want to call it, fundamentally changes quantum systems. The act of looking affects what you see, and here's where light becomes crucial. Almost all of our observations of the world are mediated by light. You see objects because photons bounce off them and enter your eyes. We detect particles in experiments by having them interact with light or leave traces that we illuminate with light. Light is the primary messenger between objects and observers. It's how the universe communicates information from one place to another. This is emergence. It's the way complex patterns arise from simple rules. It's how temperature emerges from the average kinetic energy of molecules, how fluidity emerges from the interactions of water molecules, how consciousness emerges from the interactions of neurons. The properties of the emergent system are real. Temperature is a real, measurable property, even though individual molecules don't have temperature. Consciousness is real, even though individual neurons aren't conscious. But here's the crucial insight. The emergent properties are not separate from the underlying components. Temperature is what molecules in motion feel like from the inside. Consciousness is what neural activity feels like from the inside. Similarly, matter might be what light looks like when it's organized in certain stable patterns. Electrons, protons, neutrons, atoms, molecules, solid objects, these are all emergent structures arising from the interplay of quantum fields. And those quantum fields are all fundamentally similar, all described by the same mathematical framework. Light, electromagnetic field excitations, can create matter through pair production. Matter can decay into light through annihilation. Inside protons, the mass comes mostly from the kinetic energy of massless gluons, which are like photons for the strong force. The vacuum itself is filled with virtual photons, creating virtual particle-antiparticle pairs. At the deepest level, everything is quantum fields. Some fields happen to interact with the Higgs field and gain mass. We call excitations in those fields matter. Some fields don't interact with the Higgs field. We call those force carriers, like photons, but the distinction is arbitrary. It's an emergent property of how fields interact at low energies in our current universe. At higher energies in the early universe, these distinctions didn't exist. There was just one unified field, one symmetric state. What we call light and matter are both emergent patterns in this unified field, appearing different to us because we live at low energies where symmetry is broken. But fundamentally, they're the same stuff. You are not made of atoms that are made of particles that are made of quarks. You are patterns in quantum fields, temporary stable structures in the unified field that underlies reality. And light, photons, electromagnetic radiation, these are also patterns in the same unified field. There is no fundamental distinction between you and light. You're both music played by the same instrument. Different melodies, but the same source. Let me share something personal now, because I think it's important for you to understand why these ideas matter beyond just intellectual curiosity. When I first truly grasped these concepts, when I really internalized that solid matter is an illusion, and everything is just quantum fields interacting, I went through a period of existential vertigo. If nothing is solid, if everything is just probability waves and field excitations, what does that mean for me? Am I real? Is anything real? It took me time to realize that these discoveries don't make things less real. They make reality more profound, more mysterious, more beautiful. You are real. Your experiences are real. Your thoughts and feelings are real. They're just not what you thought they were. You're not a biological machine made of atoms following deterministic rules. You're a pattern of quantum fields, entangled with the entire universe, emerging from the same unified reality that gives rise to light and time and space itself. When you look at the stars at night, photons that left those stars centuries or even millennia ago are entering your eyes, carrying information across vast distances. Those photons are connecting you directly to distant events in space-time. You're becoming entangled with ancient starlight, participating in quantum interactions that span the cosmos. When you touch another person, the electrons in your atoms and their atoms are interacting through the exchange of virtual photons. You're not just physically close. You're becoming quantum mechanically entangled at a microscopic level. The boundary between you and them blurs at the quantum scale. Everything you've ever experienced has been mediated by light. Every sight, every color, every visual memory. Light has been the messenger, bringing information from the world to your consciousness. And that light is not separate from matter. It can become matter. Matter can become it. They're two forms of the same underlying reality. This should fill you with wonder, not dread. You're not a tiny, separate being in a vast, indifferent universe. You're an intrinsic part of the universe, made of the same quantum fields as everything else, connected to everything else through entanglement and field interactions. The atoms in your body were forged in the cores of stars, created from light during nucleosynthesis, scattered through space in supernova explosions, gathered together by gravity to form new stars and planets, and eventually incorporated into living beings who can contemplate their own origins. You are literally made of stardust. But more than that, you're made of the same fundamental reality as the light from those stars. You're light that learned to think. Before we approach the end of this journey, I want you to understand something crucial. If you're feeling overwhelmed, if you're struggling to hold all these ideas in your head at once, that's completely normal. These concepts take years of study to fully grasp, and even professional physicists debate their interpretations. But here's what I want you to take away. Reality is not what it seems. The solid, stable world you experience is an emergent phenomena arising from quantum fields that are fundamentally probabilistic, interconnected, and strange. Matter and light are not separate things. They're different manifestations of the same underlying quantum field structure. This isn't just abstract philosophy. It's experimentally verified science. We've measured quantum entanglement. We've observed pair production and annihilation. We've detected virtual particles through the Casimir effect. We've split atoms and found quarks and gluons inside. We've discovered the Higgs boson. We've verified quantum tunneling. All of it is real. The universe is far stranger, far more beautiful, far more unified than our everyday experience suggests. If this journey has changed how you see reality, if you'll never look at a beam of light the same way again, hit that like button. And subscribe, because understanding reality is an ongoing journey, and I'll be here to guide you through more of it. Now, let's bring this all together. So, what if light is the true building block of atoms? Based on everything we've explored, I think the question itself is slightly wrong, but in a way that reveals a deeper truth. Light isn't the building block of atoms in the sense that atoms are made of frozen photons. That's too simplistic. But light and matter are both excitations in quantum fields, and at the most fundamental level, those fields are different aspects of a unified whole. The mass of atoms comes primarily from the kinetic energy of massless gluons, which are force carriers like photons. The tiny amount of mass that comes from quarks and electrons comes from their interaction with the Higgs field, which is just another quantum field. There's no solid substance anywhere. It's all fields and energy. Matter can transform into light through annihilation. Light can transform into matter through pair production. They're constantly doing this in the vacuum of space through virtual particle creation. The distinction between them is not fundamental. It's emergent, based on properties like mass and charge that arise from symmetry breaking at low energies. At high enough energies, like those present in the first moments after the Big Bang, the distinction between light and matter disappears entirely. There's just one unified field in a symmetric state. As the universe cooled and symmetries broke, different fields acquired different properties. Some became matter fields, some became force carrier fields, but they all came from the same source. They're all made of the same fundamental stuff, whatever that stuff is: quantum fields, information, mathematics. We don't know. That's the frontier of physics. What we do know is that light and matter are deeply, fundamentally connected. They're two sides of the same coin. Different notes in the same symphony. Different patterns in the same unified field. When ancient mystics said that everything is one, that separation is an illusion, that we're all connected, they were speaking a truth that physics is now confirming through rigorous mathematics and experimentation. Not in the vague, metaphorical way, but in a precise, testable, scientific way. You are not separate from the light entering your eyes right now. You're not separate from the stars, whose light traveled across space to reach you. You're not separate from other people, from the earth, from the cosmos. At the quantum level, you're all entangled, all part of one vast quantum system. The light you see is not different in kind from the matter you touch. They're both quantum fields. They're both probability waves. They're both excitations in the underlying structure of reality. So is light the true building block of atoms? Not exactly. But light and atoms are both built from the same thing. They're both manifestations of a deeper, unified reality that transcends the distinction between matter and energy, between particle and wave, between observer and observed. We live in a universe that is fundamentally one thing, expressing itself in infinitely many ways. Light is one expression. Matter is another. You are a third. But all of it, every single bit of it, is the universe experiencing itself, knowing itself, contemplating its own nature. When you understand this, really understand it, reality becomes more profound, not less. The fact that solid matter is made of quantum fields doesn't make it less real. It makes it miraculous. The fact that light and matter can transform into each other doesn't diminish them. It reveals their unity. You are not a tiny, insignificant speck in a vast, indifferent universe. You are the universe itself, localized, concentrated, brought to a point of self-awareness. You're made of the same quantum fields as everything else. You're connected to everything through entanglement. You're participating in the universal dance of fields and particles and waves and probability. And the light you see, the light that makes vision possible, the light from the sun and stars and light bulbs, that light is your sibling. It's made of the same fundamental reality you're made of. It's just expressing itself differently. This is what modern physics is telling us. This is where the equations lead. Reality is one. Light and matter are its expressions. And you, conscious, aware, contemplating these ideas right now, you're the universe waking up to its own nature. So the next time you see sunlight streaming through a window, or stars twinkling in the night sky, or even just the glow of a screen, remember, that light isn't separate from you.